So we're here at the Rice Northwest Museum in Hillsboro, Oregon, and we're going to be able to look at both minerals and rocks of a variety of different sort of specimen qualities. We're in the mineral property room now, and as you guys know from class, there are different things that define a mineral, right? There's 5 kind of basic things that define a mineral. A mineral has to be naturally occurring, right? It can't be man-made. It has to be solid, which means it can't be a liquid or a gas. It has to be inorganic, right? So it's not living, there's no carbon-hydrogen bonds. It has to have a distinct crystalline structure, right? So that, for example, both diamond and graphite are made of the same thing, but their structure is different, so it defines them as 2 different minerals. And then it also has to have a distinct chemical formula, right? So every single mineral has kind of its own chemical formula and then also sort of its distinct chemical structure. So different physical properties of minerals, there's a couple, right? We have color, luster, which we've talked about as being metallic or non-metallic. And if you remember, metallic means it looks like metal, not just that it's shiny. There's density, or also known as sort of specific gravity, right? A mineral that has a higher specific gravity is going to have more mass, sort of more weight for the same unit of volume. Streak, which is what color a mineral is when it's powdered. So you've probably frequently used a mineral and a streak plate and sort of ground one on the other to figure out what the mineral looks like when it's in a powder. We have crystal habit and form, which are 2 slightly different things. Crystal form has to do with the exact sort of shape of a single mineral, where habit usually refers to the external shape when it might grow in mass. We also have hardness, which is the Mohs scale of hardness. It goes from 1 at the very, very bottom to 10 at the very top. The lowest mineral as a 1 is talc, and then all the way at the top we have diamond at 10. And keep in mind this is a logarithmic scale, so that it's not just that diamond's like a little bit harder at a 10 than a 9, which is corundum. It's a lot harder, right, because it's a logarithmic scale. And we have cleavage, which has to do with how a mineral is going to break. One of the hardest things to determine, I think, with different physical properties of minerals is cleavage, because it's how it breaks, and it has to be, if a mineral has cleavage, it's going to be along specific planes. This could be one plane, which would be like a mica, like muscovite, or maybe you've seen biotite. Some minerals can have 2 planes of cleavage. A lot of feldspars have 2 planes of cleavage. And the most, some of the minerals that have the most planes of cleavage are fluorite. Here we have a beautiful fluorite crystal. And while this may look like it's a crystal form, with fluorite, this is actually its cleavage. It actually broke this way. So the way we distinguish between cleavage and form in a crystal is form is how a crystal grew, and cleavage is how a crystal broke. And so with fluorite, if you're looking at this and you're wondering how on earth does this have 4 planes of cleavage? So we can count potentially that on the bottom we have 4. 1, 2, 3, and then 4. And we have those same 4 on the top. So this piece of fluorite has 8 sides to it, but 2 of them are always in the same orientation or plane. So you have 1 plane of cleavage, 2 planes of cleavage, 3 planes of cleavage, and 4 planes of cleavage. So even though this has 8 sides, pretty much anytime you see a mineral that has multiple planes of cleavage, it's easy to identify all the sides that you think represent the cleavage and then divide that by 2, right? Because there's always 2 sides in this case that are going in the same direction. So 8 sides, but 4 planes of cleavage. And for muscovite, for example, this has one plane of cleavage. So even though this kind of top side and the bottom are two different sides, they're the same kind of plane orientation in space. So muscovite or biotite, especially when it's flaky, has just one plane of cleavage. And then calcite here, for example, kind of looks like a die that someone sat on. Maybe it's a little bit smushed, right? So this has 6 sides, right? 1, 2, 3, 4, 5, 6. So by our rule of 6 sides, that all our cleavage planes, we would divide that by 2 and have 3 planes of cleavage. We can kind of test that with 1, 2, and 3 planes of cleavage. The key here, though, is that these planes do not intersect at 90, but rather you can see that this angle right here is just a little bit larger than 90. Cool. So this is a pretty physically diagnostic physical property of cleavage, of calcite, is the cleavage planes being 3 not at 90 degrees. All right, some of the kind of other things we can think about. Obviously, we can't necessarily see hardness. Hardness is it's a diagnostic physical property of a mineral, but it's a little bit harder to demonstrate unless you can actually scratch these minerals against something. And I'd prefer not to scratch any of these nice minerals against some things like a glass plate. But to give you an idea, a glass plate sits right around a 5.5 on the hardness scale, which means that any of the minerals that are below 5 could not scratch the glass plate, rather the glass would scratch them. And then any of the minerals to the right, so 6 all the way up to 10, if we tried to scratch it on the glass plate, the glass would scratch because they are harder than the glass. So some minerals that might look similar in sort of their color and maybe their luster. For example, the 3 minerals we have here are calcite, gypsum, and quartz. And these minerals, the 3 of them, might look similar kind of in their color, right? They're colorless to maybe a little bit translucent to white. And so it could be feasible to say like, okay, well, how else could I distinguish these 3 minerals? A diagnostic physical property of calcite actually is that it effervesces or it fizzes when it comes in contact with hydrochloric acid. We don't have any hydrochloric acid present right now, so we couldn't necessarily test that. And that's probably not something you'd be able to just have on your person easily. So another way to sort of distinguish between these 3 minerals is how hard they are. If I take this glass plate, which is relatively unscratched, actually it's quite nice, and try to scratch the calcite with it, what you'll notice is the glass doesn't actually, get scratched at all, but the calcite is pretty worn down on this corner. And that's probably why it's worn down, is that people have tried to scratch it. And so now instead of being a nice sharp corner, it's kind of all ground down. So calcite isn't as hard as this glass. Quartz, on the other hand, is harder. And remember, the glass has a hardness of about 5.5 on that scale, that Mohs scale of hardness from 1 to 10. So quartz, when I try to scratch it, and this is going to be interesting, and quartz is actually pretty close to the same hardness as glass. So you do have to kind of work into it, but you can see here, oh, it's a tough noise, but the glass was scratched. So quartz is harder than glass, and this is one way to sort of distinguish between quartz and calcite without having any hydrochloric acid present. And another way also to distinguish between gypsum is gypsum frequently has these almost sort of fibrous striations in it, and it's really soft. So if I scratch into gypsum, You can actually see it's under my fingernail there. And I've been taking my vitamins, but my fingernail is still about a hardness of a 2.5. So the fact that I can kind of scratch into gypsum tells me that this mineral has a hardness below my fingernail. So less than 2.5. So if I was to line these three minerals up in terms of their hardness, I would have gypsum being lower than 2.5 because my fingernail can scratch it. I would then have calcite, which we didn't try, but my fingernail cannot scratch this. And it also cannot scratch glass. So it should tell you that it's between 2.5 and 6, right? It's harder than my fingernail, but not as hard as glass. And then quartz, which can scratch glass, is harder than 5.5. So kind of a way to give you some relative determination of different minerals that might look similar in some of their certain physical properties like color and luster, but you could distinguish because of hardness. So corundum is the name of a mineral, and even though maybe you haven't heard of the mineral corundum before, you probably have heard of rubies and sapphires. Rubies and sapphires are both gem varieties of the mineral corundum. Rubies are red and sapphires are blue. And kind of also they have more pleasing names than corundum. I think if corundum was the name of a gemstone, who knows if it would sort of sell as much as rubies and sapphires. But rubies and sapphires make really great gemstones because corundum is so hard. So corundum on that Mohs scale of hardness from 1 to 10, and again 10 is a diamond, corundum is actually a 9. So if we try to scratch this against glass really easily, you can see the glass has been scratched and the corundum is A-okay. Tough noise, I know. But you can hear that the glass itself has been scratched. So corundum itself is a 9 on that Mohs scale of hardness, and this physical property makes both rubies and sapphires excellent gemstones because they're so hard. So you don't have to worry about maybe smacking your ring if you had a ruby or a sapphire in a ring against something hard, because most likely your ruby or sapphire is harder than the surface you're potentially hitting it on. And also kind of thinking about luster, some minerals that we have here that are metallic in luster would be pyrite, galena, and hematite. So these minerals, not only, they might be shiny, but the key here is that they are metallic because they look like metal, not just that they're shiny. One kind of diagnostic feature about hematite that we said before is that when it streaks, which is when the mineral is turned to a fine powder, it actually gives a red color. So even though this is kind of gray, if we streak it, tough noise, right? Kind of gives more of a brownish red color. So very diagnostic physical property of hematite. And you can even see some of the powder on the mineral itself has that more sort of reddish. So these are all different forms of habit in here. We have, and there's lots of different sort of ways to describe crystal habit, but some can look more equant, just meaning that all sides are sort of similar. And just to give you an example, grossular here, this is a type of garnet. Microcline is a type of feldspar. And what you also may notice, especially if you are a geology major, is that looking at the ratio of silica to oxygen in some of these chemical formulas, not only can you identify that, hey, both of these minerals, for example, are silicates because their anionic group has SiO something at the end, you'd be able to identify that they're silicates, But you might also be able to identify, especially in the case of microcline, that this is actually a framework silicate, which we'll get into in a little bit. But lots of different types of crystal habits. You can have some of these more bladed minerals. This is kyanite. It's an aluminosilicate and pretty blue in color. It's one of my favorite minerals, often found in metamorphic rocks. And biotite here, so kind of scaly and micaceous, meaning that it sort of can flake off in little layers. So there's different uses of a lot of different minerals, and a lot of times when you're learning about minerals, you're also learning about mineral resources and how we use some of these things. It's easy to think about minerals being used as like jewelry, as gemstones, especially because we were talking about with like rubies and sapphires being both gem varieties of the mineral corundum. But there's also lots of other different mineral resources for, especially for things that we don't maybe think about that often. One of a sort of very common mineral that has a lot of different uses is a group of minerals that we call zeolites. Now, zeolites have sort of one really great physical property in that they're very absorbent. And so zeolites are commonly used in cat litter or anything that we want to sort of absorb certain material. For what I do as a sort of geochemist and a volcanologist, when I sample some lava flows, actually I don't like zeolites, because what zeolites will do, as we said, it's very absorbent. If I have let's say a basaltic lava that I've sampled and there were some vesicles or there were some holes present in them, and later on I had some zeolites crystallizing, it's going to be really challenging to then get a good geochemical analysis of that rock, because those zeolites, which have crystallized later on in those vesicles, have pulled in a bunch of different elements, and so it would make any geochemistry of that lava flow really confusing, because it's going to have all these additional elements in it. However, this exact thing that's frustrating for me makes zeolites really useful in sort of the larger different applications in industry. And if you have heard about and then also seen Chernobyl, which was, I think, Hulu or Netflix, I can't remember. But Chernobyl, you may have heard, if you watched the show, or you just know anything about the sort of disaster in Ukraine, that they had people eat these like specific cookies, and what they were doing was actually putting zeolites, they were crushing up zeolites and then adding them to cookies, and anyone that had been exposed to some radiation would eat the cookies, and the zeolites would preferentially absorb some of that radioactivity, and people would pass the cookie and basically sort of prevent themselves from getting more sick. So the zeolites that were in these cookies that they were eating were basically sucking out some of that radioactivity that they had been exposed to. So that's kind of one extreme of a mineral resource, but something that's very, very useful, you can imagine. And there's obviously lots of different uses of different minerals, whether it's a car battery, we talked about in certain classes, Tums, calcite being used as an antacid, fluorite, you've probably heard of fluoride being added to your water potentially. I know as a kid we had to take like fluoride shots and some fluoride was added to water. Gypsum has been used for drywall, right? There's all these different uses, from magnets to copper wiring to car batteries, and obviously jewelry. But I do think one of the most kind of interesting ones is thinking about zeolites as being a very powerful absorbent. Cool, now you know. So one of those five defining features of a mineral, we said mineral has to be solid, inorganic, naturally occurring, a distinct chemical composition, and also an ordered arrangement of atoms, where that distinct chemical composition is the mineral formula, and the ordered arrangement of atoms is the mineral structure. So in that, with the chemical formula, a mineral is going to have a specific sort of anionic group, or a group of elements that hang off the end of the chemical formula, and we can distinguish which type of mineral a mineral might be based on those elements. So the different groups that we have of these different mineral types, depending on that anionic group, can be basically as simple as a native element. So this is going to be things like gold, silver, bismuth. So these are just one element that make up a mineral. Most of the minerals that kind of we've been seeing are silicates. So they have silicon and oxygen hanging off the end of that chemical formula. But we can also have sulfides, which just has a sulfur hanging off the end, oxides, which typically has oxygen, sulfates, which will have sulfur and oxygen, carbonates, carbon and oxygen, hydroxides, halides, phosphates, tungstates, and borates. So there's all these different types of anionic groups that we can sort of help distinguish different minerals. And again, most of what we're going to be seeing in lab are silicates. But we do have some minerals such as pyrite, which is a sulfide because the chemical formula is iron, Fe, and then S2. So that's a sulfide. Galena, do we have galena over here? Yeah. So galena is Pb, lead sulfide, so PbS. And most sulfide and oxide minerals tend to, there's a number of them that can form together, whereas many silicate minerals will sort of form together. Silicates, which this entire right-hand side is dedicated to, can be further subdivided depending on how many silicon atoms you have to an oxygen atom. The most sort of common one, potentially, or when you think of like quartz and feldspar, these are both framework silicates, and these are also known as tectosilicates, and quartz and feldspar are both tectosilicates. And what this means for a silica tetrahedra is that every single oxygen in that tetrahedra is bridged or shared to another tetrahedra. And this is why quartz and feldspar are so resistant to weathering, is because every single one of those oxygens is bridged, and so it makes it like really, really stable. It's also why in magmas that have more of a higher basically silica content, it's because those oxygens are all shared, and so it makes it like much more viscous and much more resistant to flow because everything is sort of much more interconnected. We also have phyllosilicates, also known as sheet silicates, and so our micas, like our muscovite, biotite, are both sheet silicates. Inosilicates, which are chain silicates, and this can be either single chain or double chain. Our single chain silicates are our pyroxenes, and our double chain silicates are our amphibols. We have cyclosilicates, also known as ring silicates. This includes the mineral beryl. And beryl is also the mineral family where you get the gem variety of aquamarine and also emerald, right? They're just sort of the gem variety of the mineral beryl, which is a cyclosilicate. And we have nesosilicates, which tend to basically, you can see in this little photo, there's no bridging between the oxygens. And so olivine is a good example of a nesosilicate. And we have some disilicates, also known as sorosilicates, and in this case, an oxygen is only shared between two of those silica tetrahedras. And of course, the silica tetrahedra has a silicon atom in the center with 4 oxygens around it. And again, the more oxygens that are shared, the more resistant to weathering the mineral will typically be. So quartz and feldspar are relatively resistant to weathering because they are framework silicates, also known as tectosilicates, and every single one of those oxygens is shared with another tetrahedra. Pretty cool. And while they're not present on some of these minerals, because some of these specimens are, really high quality, maybe you saw on a few minerals that you can actually see their chemical formula in them, and thinking about that formula, looking at those elements that are on the end to tell you something about whether it's a silicate mineral, a sulfide mineral, a carbonate mineral. And so breaking minerals apart sort of based on their chemical formula, that anionic group, is very useful because it also allows us to be predictive about what two minerals may form together.